Let me see if I can't share the screen here. So yeah, by the way, when I worked at Intel, I was down in Chandler, Arizona. So I was down in Phoenix for about 4 years and I missed the weather. It's kind of a chilly morning here in Missouri, but thank you for the invitation. I'm quite happy to be here today to talk about some of the latest research going on in my group. Sorry, I'm kind of fumbling. There you go. So yeah, the discussion today is going to be towards autonomous materials in experimentation, and more specifically, my applications towards carbon nanotubes and carbon nanotube forests. And so the word towards there, I think, is kind of important because we're not totally there yet, but we're working towards it. And so bottom line up front, this is the system that we're working towards. So my group does a lot with carbon nanotube forests, and carbon nanotube forests are nothing more than, I'll say densely populated, but populations of carbon nanotubes that grow concurrently. And as they do, they kind of push each other up, they self-assemble into a film. And it's ultimately one route to potentially scaling carbon nanotube synthesis. And so there's a lot of unsolved questions remaining in terms of how to create these carbon nanotube materials with the properties that you want. And in fact, there's orders of magnitude, I think, of potential still there. But overall, what we want to do is create I'll just call it a system that can conduct research for us without the user in the loop. And so by that, I mean a system that can conduct experiments, whether physical or numerical. And as it's conducting experiments, it'll learn from the experiments and it'll march towards some sort of objective function that we give it. All right, so here's a brief introduction of what I'm going to talk about. So I'm going to talk a little bit about CNTs in general, and then I'm going to talk about the elements of our system design. So those are, simulation, in-situ growth of carbon nanotube forests, some of our initial machine learning, and then kind of talk about this vision towards autonomous research. Just a little bit about me. I deal heavily with nanoscale manufacturing. So like I said before, I do a lot with carbon nanotubes and more specifically carbon nanotube forests. And I look at their mechanics of self-assembly. So I look at more than just synthesis. So we do interesting machining after the fact, after growth. Like I said, there's simulation. Recently, we've been getting into some area selective atomic layer deposition, and that's the last picture on the top row. I also have within the last couple of years, become involved in nanoenergetic materials, and more specifically nano thermites. So these are nanoscale particles, solid state particles, that once you initiate reaction, they react and they're very exothermic. So you can get reactions 3,000–4,000 Kelvin. So interesting system. And if I have time at the end, and I doubt I will, I can talk about efforts in that area. But also more so when I was coming up as a grad student, really my focus was on thermal transport. And so I'm getting more and more into thermal transport as I go along in my career here as well. But one thing that all of these experiments have in common, and you can probably relate, especially if you're an experimentalist, the iteration of these experiments is quite slow. So specifically for my nanotube experiments, I have to do an experiment of synthesis one day, I'll characterize it a different day, I'll analyze the results maybe sometime down the road, and there's probably gaps in between. So it takes a long time. And so I was introduced to this, what's called the Gartner hype cycle, and I really like it. So this is, if you look at the axes of this plot, you have expectation versus time. And I like to say also, this is probably like grad student motivation with time follows a similar trend. But if you look I'll explain it here in a second, but if you look down, let me see if I can get my laser pointer. Here we go. If you look down here towards the text at the bottom, there's these interesting words that kind of describe what's going on. So you've got an innovation material. So this is valid for technologies, not just materials, for technologies in general. Somebody discovers something, it's really, really exciting. Expectations increase, it's going to change the world. You reach this peak of inflated expectations. I love the phraseology here. And then you enter, the expectations go down. Well, maybe it's not going to be as great as we thought. And you enter this trough of disillusionment, which is just hilarious to me. So, this is the point where, gosh, maybe all of our expectations weren't met. This is harder than we thought it was going to be. but then you kind of sludge through and things start getting better and better and better. And you enter the slope of enlightenment and you enter this plateau of productivity. Really interesting chart. And this company, Gartner, actually maps technologies year by year so you can see them. So the interesting thing is, for materials, we've got, within the last couple of decades, really interesting tools, both numerical and physical, that we can employ in a bunch of different areas. So synthesis, characterization, things are accelerating in terms of what we can do, but the speed at which we do our research isn't really changing. So Dr. Benji Maruyama, who works at the Air Force Research Lab, I actually worked with him for a while, proposed this Moore's Law for the speed of research. So Moore's Law, I'm sure everybody's familiar, but essentially every 18 months to 24 months, the speed of CPUs was increasing because the number density of CPUs was increasing. But when you stop and think about it, we're still doing the same kind of things that we were doing generations ago. So we have these cook and look kind of experiments, where everything's kind of hidden for us. We put something into a system, it comes out, we look at it, we don't really know what happened in between. We're still kind of Edisonian in our approach. It still takes about 20 years from the discovery of a material before it's really entering maybe into the marketplace. So things are slow. Why can't we do something to increase the speed of research? And so that's what I'm going to talk about. And so notice the name on the quote, that's Dr. Benji Maruyama. So he did something about it. And he works in the field of carbon nanotubes. This is a paper released in early 2012, where he's kind of making inroads, the first inroads towards autonomous experiments. This exact paper isn't autonomous, but if you go to the right, you'll notice that he was very intentional in his design of this reaction experiment. So let me describe what's going on. So like I said, he's researching carbon nanotubes, and he came up with an experimental platform that's really, really smart. So he's interested in single wall carbon nanotubes, and his experimental platform consists, if you look at the figure, of many, many different silicon pillars that have an insulating silicon dioxide layer at the bottom of the pillars. And so he's conducting experiments within a Raman spectrometer. And so his laser is powerful enough for the spectrometer that he can heat the top of this pillar where carbon nanotube catalyst resides. So it's typically just a thin layer of iron. And so the laser supplies heat to the catalyst, and the whole system is enclosed, so he can flow hydrocarbon gases through, and he can facilitate a chemical vapor deposition process. And so he can grow carbon nanotubes, isolated carbon nanotubes on the top of these pillars. And as he's doing it, he can use a spectrometer to measure things like the temperature of the silicon pillar, the chirality of the carbon nanotubes themselves. They're single-walled carbon nanotubes, so he can specify exactly what the product is. And he can also integrate this G peak. There's a lot of lag on my system for some reason, but this G peak, if you look at this cascade plot, is growing. If you integrate that, that's an indication of a growth rate. And so he devised this experiment. This is not autonomous at all. This is a human-controlled experiment. But he was marching towards autonomous experiments, which I'll show in the next slide. But even with this really interesting experiment, he was able to get this Nature Materials paper where he was able to say something about the growth rate of single-wall carbon nanotube as a function of their chirality. So just this experimental setup alone was really unique, and he was able to say something about a problem of interest to the community. So again, this was January 2012. Fast forward now over 4.5 years, and now he's using that same system for autonomy. And so what does this mean? So actually, let me show the plot here. Yeah. So he's using this system where he can track all of these parameters, and he's got control over temperature. He's got control of pressure and gases that he's applying into the system. And he integrates everything together along with an artificial intelligence planner such that the experiments can start conducting themselves and learning as the experiments are being conducted. And so this is another nature-based publication, MPJ Computational Materials, where this is his first demonstration of autonomy. He says his group inputs nothing more than a growth rate objective. without specifying how the system can get there. And so the autonomous system starts launching experiments and learning from experiments and mapping out the complex process structure kind of relationships going on. And so as he sets these objective functions and the number of experiments increase, I don't know why there's so much lag here, but if you can see my laser pointer, the experiments start converging to the desired growth rate set by the user without any user input whatsoever. And so you can see the user start jogging this growth rate to different growth rates. It's in a log scale. So they're actually varying the growth rate objective function over orders of magnitude. And the bottom plot basically shows that from task number 3 to task number 10, the experimental planner needed fewer experiments to reach its objective function. So it's pretty neat. So it's the first demonstration, at least in the community that I know of, where the user was out of the loop, the experiments conducted themselves and learned from themselves so that they could reach this desired objective function of growth rate. So that was pretty neat. And that actually inspired me. Like I said, I was working with carbon nanotube forests to do something quite similar. So what are carbon nanotube forests? Like I said before, they're just populations of carbon nanotubes that when they grow together, they more or less force each other upward into these films. So what I'm showing to the left, this is an image by a particular company where they're growing centimeter scale carbon nanotube forests. So this black pillar here is many carbon nanotubes that grew to a centimeter length. And so carbon nanotubes and carbon nanotube forests are typically grown by chemical vapor deposition. So you need high temperature, you need a hydrocarbon gas, you need a catalyst. These are the core elements of growing carbon nanotubes. And even though that looks very dense on the left, if you use an electron microscope, you can see they're actually like 1 to 5% dense by volume. And so if you boil that down into like a number density, we're talking 10 to the 9th, 10 to the 10th carbon nanotubes per square centimeter for a typical multi-whorl carbon nanotube forest. And so these things can be patterned. What I'm showing here is something that we did a couple of years ago, where you can pattern them in 3D. And this is done nothing more than by catalyst engineering, patterning where the catalyst is and what the catalyst composition is. You can spin these things into yarns. So just like you would with wool, if you grab an edge and the van der Waals forces are sufficiently strong, you can just pull and pull and pull and form a very conductive high strength yarn. So it's an interesting material. And I'm showing here, in my past life, I guess, at the Air Force Research Lab, I was really concerned about the mechanical properties of carbon nanotube forests. And if you think of carbon nanotubes, if you know anything about them, one of the claims to fame is that they're very stiff and rigid. And so they've got an elastic modulus that's on the order of terapascals. And so that's kind of relatable to diamond, right? So if you relate that to hardness, diamond's extraordinarily hard. And that's something that we're a little bit more familiar with on the macro scale. So what happens when you grow carbon nanotubes in these forests? Well, you can see this is a log plot. The elastic modulus drops by like 5 orders of magnitude. It's a really substantial drop off, even when you consider the fact that it's not 100% dense. Okay, and actually CNTs, an individual CNT is like diamond. When you grow them all together in this population, the properties are more like natural rubber. So just kind of a vantage point that maybe you're more familiar with. So what's going on there? We don't know. There's a lot of unanswered questions, but I think there's a real opportunity here where if we can get the conditions correct, we've got a large technological envelope where we can operate just using carbon nanotubes alone. So it's an interesting problem. And so as we're trying to march towards this autonomous system that can grow and characterize carbon nanotubes for us and learn, one of the things we need to consider is, as we're growing the system, we need to be very intentional. So there's various ways that you can characterize carbon nanotube forests. So the most common is by SEM. So SEM gives you images like this. The advantages are it's available, it's fast, there's a pretty big depth of field, and you can see certain things within the carbon nanotube forest. You can extract things out at least qualitatively. And right now, if you were to look at this image, you can't tell me really a good density distribution for the nanotubes. You can't tell me what the areal density is. You just can't. So I think there's an opportunity here if we can get the methods correct, that we can use machine learning maybe to take SEM imagery and extract these parameters later on down the road. So that's just kind of a sneak peek at where I'm going here. Another way is small angle X-ray scattering. So this is a very powerful technique. Unfortunately, you need a synchrotron to make it work. But this is something that John Hart, who is now up at MIT, really pioneered and got some very useful information from this technique. So the way it works is you have a very focused high intensity X-ray beam. It penetrates through your carbon nanotubes, and you looked at the scattering pattern, and you can extract a lot of parameters. So one thing that's pretty readily easy that you can measure is carbon nanotube density as a function of height, essentially, so distance from the top surface. And one thing that folks really haven't understood in the community, but we can look at it and see, is that carbon nanotube density degrades quite a bit as you go from the top to the bottom near the substrate. And so here's some examples of that in the plot to the left. Okay, another thing that you can characterize is relative carbon nanotube alignment. So from the scattering patterns, you can use Hermann orientation factor, and you can say something about how, as a population, the carbon nanotubes are aligned relative to the perpendicular axis. And so it's a more powerful technique. You can extract more quantitatively, diameter alignment and even density. And you can even use it in situ. So you can use this technique as the carbon nanotubes are growing across your X-ray beam. So that's pretty nice. So on the downside, you need a very high power photon source. So that's not readily available. And you're sampling, I did this calculation this morning, actually, something like 500,000 carbon nanotubes in this process. So you can say something on a population basis. You can't really say anything on the individual CNT to CNT interactions. So powerful, but maybe not so useful if we want to start thinking about in situ techniques. So this is a really neat one. So this is in situ TEM, transmission electron microscope synthesis. So in this case, this is transmission electron microscopy. We're watching carbon nanotubes as they grow within an environmental TEM. And you can certainly see things going on. You can see the outline of the carbon nanotubes. You can get a sense for their density and their diameter. The bad news is with this technique, because we're looking at a projection, it's really difficult to know. I'll launch that again if I can. It's really difficult to know what's going on in 3D. And so each of these techniques has pros and cons, obviously, but it's not quite suitable for what I wanted to do with carbon nanotube forests. And so we can extract data with this. And for me personally, I think it's really interesting just watching these kind of videos, and the fact that we can run these experiments now is quite interesting. All right, so last but not least, that's characterizing the synthesis and the structure of carbon nanotubes. We can also, like I said before, I used to be very concerned about mechanical properties. We can do compression testing of these carbon nanotube forests, and they give you beautiful compression patterns. So you can see this coordinated buckling that occurs at the bottom. And if you were looking at the force versus displacement profile, you would see that these materials deform quite a bit like foam. So there's an elastic region and a plateau region as these buckles form, and they can absorb quite a bit of energy. And something that's kind of interesting here, just an FYI really, but you can apply digital image correlation, and you can track the strain in these materials as they're being deformed using just SEM images. So pretty interesting stuff. These are the kind of things that I would like to understand, but do it all autonomously without having a human in the loop. And so the big question is, overall, these experiments, I think even if we were to get an autonomous system going, for carbon nanotube forests, it's very slow. So, you know, a couple of experiments per day are possible in a good day. So an overarching question of mine was, can we develop a simulation that can look at all of these processes and capture the physics, you know, at least to first order? And that would allow us to, you know, so like I said, the experiments are costly and slow. Experiments are cheap and parallel. So I think you can do a lot of interrogation with experiments that you can't do with physical experiments. And so the group devised this finite element simulation. I don't know why I couldn't think of simulation, but it's a dynamic simulation that we can use to look at the growth of carbon nanotubes, but then also interrogate them in all these similar ways as we could with a physical experiment. And so these are just finite element frame elements where we have, in the case of 2 dimensions, 3 degrees of freedom at each node. And we can just stack element by element to simulate growth as a function of time. And as these carbon nanotubes come into contact, they're held in contact by van der Waals forces that we can just simulate as a simple spring. But then we can march through time and we can look at, here's a synthesis video in 2D. You can see we start capturing, at least to first order, some of these wavy and straight features that we saw in an SEM image of carbon nanotube forests. So this was work that we did several years back now. But this gave us some confidence that this was maybe a good path to pursue, because like I said, we were capturing these first order effects. And not only that, these experiments allow us to measure things that we can't measure experimentally with a physical experiment. So if I were to ask what's, for example, the stress on the catalyst particle that resides at the bottom of each of these carbon nanotubes, you couldn't answer that with a physical experiment, whereas numerically you certainly could. And so you can do the synthesis experiment. You can also come along and do the compression experiments. And because it's numerical, you can do whatever you want. You can compress them in the axial direction. You can compress them in the transverse direction. And along the way, you can get these force versus displacement curves. So I'm showing the simulated results here. The axial compression, when I was compressing down against the long axis, you get the response in black, and that's a classic foam-like response. And it's quite a bit softer if I compress it in 90 degrees in the transverse direction. So that's interesting, but we were actually able to perform experiments using some of these nanotube forest pillars where we can actually do these experiments in the axial direction and the transverse experiment. And again, at least to first order, this was a 2-dimensional simulation, but at least to first order, we're getting the kinds of qualitative results that we would expect. So this was, again, another positive sign that we were doing something correct with these simulations. And it's worth noting, I think, that all of the inputs that we were feeding to these simulations are extraordinarily simple. So we'd have like a Gaussian profile of the growth rate. So we'd input an average growth rate. All of the nanotubes you're seeing here are simulated as having the same diameter, which physically isn't true. But we can also grow them with whatever population that we want, honestly. But these results were all like the simplest possible things that we could throw at the simulation, and it was giving us some pretty good results. So as things were maturing, we really wanted to link the simulation with experiments as best as we could. And so here's an interesting experiment that we did with the Air Force Research Lab. They've got a test rig at the Air Force Research Lab that you could put in an SEM, and it can perform mechanical experiments. And so we were curious. So we typically deal a lot with these carbon nanotube microstructures that you're seeing here. So at the left, at the far left of the image, you can see this is like a monolithic carbon nanotube pillar, and it's got a circular cross section. You can grow the cross section however, whatever geometry that you want. So in the top right, these are our carbon nanotube pillars that were grown vertically, and they've got a square cross section. And so I showed you compression videos before, and one summer we had the idea, what if we tried to do some delamination experiments with these carbon nanotube forests? Because we know that they're not anchored extremely well to the surface, but it's quite difficult to quantify what that delamination stress is. And so what we did, if you look at the figure to the left, we put a drop of fast curing epoxy on a nano indenter tip. And as it was still wet, we came down and made intimate contact with the top of one of these CNT pillars. And then we waited for a couple hours for that epoxy to cure. And then once it was cured, we backed that indenter tip upwards, and we were able to measure as a function of time here what the tensile stress was, and ultimately what the delamination stress was. And so if we treat the pillar as a monolith, the tensile stress was something like 3 megapascals on average. And so That's good information. And I think that was probably at least at that time, and I think it still is, probably the best measurement of one of these carbon nanotube forests with respect to delamination. But if you recall, I said that these things are a couple percent dense by volume. And so as you lift these things, you can see here at the bottom right that there's kind of residue left from where the nanotubes were. And also there's some shorter nanotubes that were left behind. And all of that, kind of in your mind, you might think, well, what's the actual stress at the bottom of the carbon nanotubes that are interfacing with the substrate? And so this is a good application, I think, of our simulation. So we took it to the simulation and we did a growth. I think this was, I forget exactly, but 3 or 5 times 10 to the 9th carbon nanotubes per square centimeter equivalent, which is what this recipe should yield. And we just let it grow with the properties that we would expect of this kind of carbon nanotube. And then we were able to quite easily apply a tensile load to the top surface. And what you're seeing here is an evolution of stress at the bottom left at the interface of these carbon nanotubes with the substrate. And so what we were able to find is, although it was 3 megapascals, if we treat it as a monolith, if you translate that stress back down to an individual interface between carbon nanotube and substrate, that adhesion stress is more like 350 megapascals. So this was a good application of our simulation that we could link back to experiments. And this is where we are now. So this is work in progress, but we've since transitioned this simulation to 3D. And this is where my excitement lies right now. So you're watching kind of a real-time evolution of morphology from one of these simulations. And you can see a couple of things. When it's done, you'll see this. It matches fairly well with the morphology of carbon nanotube forests that we grow experimentally. And that's no small victory in my mind. A couple things that it captures. If you look at the top, it's still growing. Once this is done, you'll see the top, which is really what we were trying to capture here. The top surface of the simulated carbon nanotube forest is pretty similar to what you'd see with the experimental carbon nanotube forest. So towards the tips, they're more or less vertical. And then they enter this region where there's quite a bit of disorder. And then that disorder tends to relax a little bit as you go downward towards the substrate. And so qualitatively, that's nice. And the way that we were able to achieve this was applying the results from the previous slide, which was a adhesion stress of something like 350 megapascals at the bottom of the carbon nanotube. So as these nanotubes are growing, they're competing mechanically with one another. And we're saying that if the tensile load ever exceeds 350 megapascals, we're going to lift that nanotube off the surface, and it's just going to float with the rest of the nanotubes as the growth process continues. Okay, so we were able to capture this crust layer, which people refer to it as, but it's this kind of dense, disorganized layer at the top of carbon nanotube forests. So that's really exciting. Again, everything that we're throwing in this model is as first order as we possibly could. And we're recreating events pretty darn well based on these like post-synthesis images. And really what we want, if we think back to an autonomous system, is that we want a digital twin. And so this is kind of an exciting word, I think, not just a simulation, but a simulation that really holds up and can be interrogated just like a physical material could. So with these simulations, we can run thermal conductivity tests, electrical tests, mechanical tests. We can run a small angle X-ray scattering if we wanted to simulation. So we really want a digital twin because we can run these experiments in parallel. We can do them pretty quickly, and we can iterate and learn much faster than we can with physical experiments. So this is a key element to our autonomous research robot vision as we're going forward. All right, so I was saying that you can make measurements. It's not just interesting pictures. You can make these measurements as you go with simulations that are going to be very difficult to do outside of simulations. But one thing that we can match experimentally is the decay rate of carbon nanotubes as they're growing. And so if you look at the middle column there, we've seen the inset image before. So this is carbon nanotube density as a function of height that was measured using small angle X-ray scattering. And this is kind of hot off the presses. I almost didn't show it today. But this is our initial results as they're still building here. And we're seeing kind of a similar decay rate. But this is very preliminary results. But what we want to do is match our simulation results so that we can mirror what's been shown experimentally. Again, we're building the fidelity of this model so that it can stand as a digital twin to experiments. And another thing that we're measuring here, so this is measuring the growth rate of carbon nanotubes as a function of height. And so what we're seeing is that the slowest growing carbon nanotubes, as you might expect, are delaminating first, leaving behind the more quickly growing carbon nanotubes within the population. And this blue line here represents the population average, which is 60 nanometers per time step. So the slower growing nanotubes within the population are being delaminated first, leaving the faster growing carbon nanotubes behind. And so this is something that we're building. And the reason that we're building is because eventually we want to meet up with in situ SEM experiments that we can use to validate the model. And so again, simulation, I see bigger picture wise, we can use it for rapid hypothesis testing. So I can integrate into it whatever growth kinetics I want, whatever mechanical feedback to a catalyst particle, whatever. So it's very, very flexible, but we have to get the first order things correct before we proceed to these more complex situations. And so not only can we grow, but we can do this entire process structure property paradigm where we can interrogate from start to finish like the simulation is a virtual laboratory. And not only that, we can use it for machine learning, which I'll talk about next. And I think the exciting tie-in here is that we can simulate exact replicas of scanning electron microscope images that I'll show you next. So if I have a particle field that I'm using for my scanning electron microscope experiments, I can simulate exactly that catalyst particle field with experiment and see how they match. So again, this is all towards a digital twin. So let me check time here. So this is all meeting up with in situ experiments that we're performing. So this has been really complicated, but we're finally lifting this off the ground. So what we're doing is we saw the TEM version before. We're the first group to really grow robust carbon nanotube forests within a scanning electron microscope. And so the way that we do this is basically the microscope becomes your chemical vapor deposition furnace. This is an environmental SEM, which means that we can introduce gases within the system without harming the system. And so we're introducing acetylene gas at a pressure between 10 and 50 pascals. And within the chamber, we have the fixture that you can see at the bottom left. So this is a special fixture from Protochips. It's a company. And it's not present here, but right here where this hole is, there's a MEMS heating device. It's just a consumable chip that you would then place on that holder, and it heats up. So it heats up locally if you go to the right bottom image here. This is what the protochip itself looks like. So there's electrical contacts, and it's heating up a very small portion of that chip. So something like 100 by 100 microns is the actual uniform heated zone on this chip. So we'll heat up the chip on that chip before we load it into the SEM. We'll have all the catalysts that we need, and then we'll introduce the gas, and we can watch the process occur, the process of carbon nanotube synthesis as it occurs. And this is, so if you remember back to the SEM images, what I really want to understand is the self-assembly mechanics of these carbon nanotube forests, because that's at the root of all the properties that we're going to care about. And so SEM affords us that opportunity to see these mechanics. We saw that with TEM, you basically see through the nanotubes, and you don't get a good sense of how they're interacting. All right, so along the way, these are surprises. It's been a real journey here. So one thing that we noticed is early on with these experiments, we had terrible luck. We've probably gone through hundreds of these protochips by now. But one thing that we saw by accident is that when we were depositing carbon on these chips, so if you know much about electron microscopy, where your beam interacts with your sample, especially if your chamber is kind of a general use dirty instrument, you're going to deposit carbon, whether you want to or not. And so that's called adventitious carbon. We were noticing that our catalyst nanoparticles were forming and carbon nanotubes were being synthesized only within these square regions where we were depositing this carbon. And why were we depositing the carbon? Because before we started our experiments, we would focus in with the electron beam to get as good of an image as we can. So we were dwelling in one region for a significant amount of time. And as we were doing that, we were unintentionally putting down this thin carbon layer. And so actually after the fact, it's not a big surprise because within the past couple of years, researchers in the field have noticed that carbon itself reduces an iron. So we're using iron catalysts, and as we transfer the iron catalysts in the environment into our SEM chamber, the iron's going to oxidize. So we actually have iron oxide. And the first step in the CNT synthesis is reducing that iron oxide into metallic iron. And so it turns out carbon is a very, very effective reducing agent for iron oxide. And so we get these particles to preferentially form. The carbon nanotubes themselves form directly on those catalyst particles as they form. And at the right here, you can see these little squares where we were doing focusing experiments. And you can see in this particular one, we had a nanotube forest. We're looking at an angle here, but this one was about 100 microns in length. Okay, so it's an interesting problem, but man, it caused us a lot of problems, and it still does. We're trying to understand it. Turns out this is actually a really interesting natural convection problem because we have a very isolated 100 by 100 micron square. It's in a quiescent environment where we don't have any bulk flow. And it turns out at the pressures where we're operating, the mean free path of the gas is like 30 microns, which is about the same size as our heated zone. So I think what's happening is we might be forming unintentionally like a stagnation point where our hydrocarbons can't get down to our heated zone to perform the reactions. And we've seen some evidence of that. If you look at this figure labeled as A at the bottom, we get this kind of stadium growth around the heated zone. If we nuke our chip and send it to like 1200 degrees C, the region outside of our uniform heated zone heats up to an appropriate growth condition of like 600 or 700 degrees C. And we see that outside of this central heated zone, we're starting to get this concentric growth. And we would expect in that region that we wouldn't necessarily have a stagnation point. So we're working to understand that better. And that all by itself is kind of an interesting problem. But I'll show you here some interesting videos that we've gotten. So here's catalyst evolution. Hopefully it comes through in Zoom. But you can see all these little particles that are forming and moving around. And they're forming larger and larger particles. So this is known as Oswald ripening. And it's a known phenomena. And it occurs even as carbon nanotubes themselves are growing. So here's a successful kind of large scale synthesis of carbon nanotube forests. So you can see that square pattern, that's where we intentionally deposit carbon. And the grad students got excited and they got interesting images out of this, which is great, but they're not of much use to us as we want to validate our model because the magnification isn't high enough, okay? So I'm kind of going fast because I know I'm kind of running out of time here. But here's a better experiment where we can start seeing the root of the carbon nanotubes where the growth is occurring and the self-assembly is happening. This was a swing and a miss, but boy, we're close to getting exactly what we want. Where you can't really resolve the interactions quite yet where we want towards the substrate, but we're very close. And I think we can optimize our image acquisition conditions to get where we want to be. And so the vision is we're going to have this experimental capability where we can view what's going on in real time with our carbon nanotube forest as the synthesis is occurring. Can we use our experiments or our simulations rather as this digital twin? Once we validate our simulations with this experimental observations that we can see with this kind of in situ growth, can we then take a one-to-one matchup where once we see the particles form, can we then convey that information to our simulations and have the simulations try to mimic exactly what's going to go on in an experiment? So that's kind of an exciting thing. And so Let me check my time again. I'm running long, apologies. But again, so here's what I showed earlier. You can see the in situ synthesis is on the left, but again, that's going to be kind of a slow, low volume kind of a process. So what we want to do is merge the SEM in situ growth with our higher volume simulations to see if we can't train machine learning and extract the relevant physics that we need to really understand the core kinetics of what's going on with the process. Okay, so in my last couple of minutes here, I'll show you what's going on with the machine learning, because we just had a paper release that I'd want to talk about with respect to machine learning. So machine learning was, well, obviously you need quite a bit of data to do it. So we used our two-dimensional simulations to come up with 22,000 plus experiments where we were growing carbon nanotubes and then compressing them. And we would run those carbon nanotube images through a supervised learning algorithm, the VGG19 transfer learning. And what we were trying to predict is, based on various input conditions that we would feed to the model, could the machine learning algorithm discern what those process parameters were? So things like diameter, density, the growth rate variation. Based on images, could the deep learning algorithm give us, predict what those parameters were? The answer is it did a pretty good job. And not only that, we were running these compression experiments. So could we then extract the mechanical properties that we care about, things like stiffness and a buckling yield? And so I'll just show some results. So here's what we gave it 63 different classes of materials. And the 63 classes are comprised of different densities, different CNT radii, and then different population growth rate variations. And so we've got in this mosaic an example of all 63 classes. And it turns out, even though like the human eye would look at them and say, wow, that's a bunch of squiggly lines, the machine learning could look at those squiggly lines and extract out for us what the number density was, what the radius was, and what the variation was in our simulation. And at least for density, for diameter, even though the diameter in the simulation was changing, as we were generating plots, they were all plotted with the same diameter. So the machine learning was extracting those parameters just on the morphology behavior. So I'll skip this slide. Here's the kicker. So with our classification, we were over 91% accurate in predicting both density, diameter, and growth rate. And with respect to stiffness, we had very good agreement, and we were able to, based on images alone, predict the mechanical properties better than a linear regression based on the actual data gave us. So that was pretty exciting for us. And again, this was just released a couple months ago, that paper. And so again, this will be my last slide, back to the big picture. What we want to do is create this autonomous experiment that can launch these in situ SEM experiments. It can launch the simulations. And as it goes, just like the single carbon nanotube experiments that I opened up with, can we run these digital and physical experiments and have in the background a machine learning algorithm understand the linkages between all the input parameters and the properties that we want to measure, so that we can explore that large envelope in potential technological envelope, really, that's available to us. Because right now we can't, and everybody's kind of stuck in a silo. And I think that the machine learning algorithm is going to give us new recipes that we wouldn't have thought of with our conventional human biases. And so as we're putting these pieces together, this last part at the bottom of the figure is actually critically important. We need to crawl before we can run. So we're going to have to first kind of supervise the process. And this is an interesting part of the problem all by itself, but we have to eventually, in steps, allow the system to take full control while the user has less and less control before the user is completely out of the loop. So I ran long with time, so I'll just skip over these things. Thank you very much for your time. My apologies that I went long. But you can see here the collaborators, and I'll just open it up for some questions.
Thank you, Matt. This is very, very interesting. Do we have any questions from the audience?
Yeah, I have one.
Yeah. Yeah, go ahead.
Hi, Dr. Maschmann.
Yeah, hi.
So my question is, what are the representations you use to model your CNT so that you can measure the deviation of the simulation result from the experimental ones?
So you're talking about the machine learning thing at the end?
Yeah, but more on the representation side, right? The way I look at it, sorry, I'm an outsider of this, so I'm seeing like a candy cloud. So how do you represent the system so that you can, measure the difference from your simulation to your experiments? I assume you're not going to measure every single tube, right? The geometry of every single tube. So how do you come up with a some kind of I don't know, maybe statistical description of the forest?
Well, so everything's going to be image based. So our plan is to just import images, and based on the image data alone, we can extract everything that we need. And if that's successful, kind of a grand picture would be not only predicting these carbon nanotube properties, like mechanical properties, thermal properties, what have you, but even above and beyond that, if we can get good at this, we could have an add-on package to like an SEM user, so that as they're imaging their carbon nanotube forests, the machine learning can extract out for them, this is the number density, this is the diameter distribution that we foresee based on your images that you're looking at, because otherwise that's inaccessible. But what we're feeding in is nothing more than images.
Okay, yeah, I understand on the machine learning part, you are you're sort of characterizing the simulation based on the images, right?
That's right.
But from the experimental side, will you be able to also take these 3D scans of the actual growth of the forest and then also characterize them based on the 3D model? So
that's in the plans. Can we do it? Yes, I think we can. How well we can do it is the question. So Felice Bunyak, if you look here in the machine learning collaborators, she's like a computer vision kind of a specialist, and this is going to be her role. And so we're just really engaging together in this project, because we're just now at the point where I think we're going to have meaningful 3D simulations, and we're going to have meaningful experimental data. But the plan is, yeah. So what are the metrics to compare? It's going to be challenging, and I don't fully know the answers to that. That's not really my field. But the intent is to, yes, as best we can, match visually the representation of a physical and a numerical experiment.
I see. Okay.
Yeah,
thank you.
How that's going to happen, that's kind of beyond my expertise level. So I'm relying on collaborators to help with that.
Okay. Okay. I guess we can talk more about it during the discussion.
Yeah, sure.
Thank you.
Can I ask the next question?
Sure.
Hi, my name is Harsono Simka. I work for Samsung Electronics, Samsung Semiconductor. I lead a small research group here in San Jose, California. So, Professor Maschmann, I'm really happy to see your presentation. I feel like I'm a kid in a candy store. Like in your Gartner chart, I'm probably, in the left region where it's still a hockey stick, and excitement building up exponentially.
Right. Sure.
So I think from, I come from the semiconductor processing field where, we deal more with small interfaces, nanoscale materials, right? But we also care about 1D and 2D materials, such as carbon nanotubes, right? but the applications, as you can imagine, is very different, right? So so my first question is that we care about things such as uniformity in the tubes to be deposited, right? So that we could use it as an electronic switching device, right? As in a semiconductor channel. So we care about size distribution. We care about the properties of the nanotube. We want all to be semiconductors instead of metallic, right? And we care about their density in different areas, right? We want to be able to predict how many nanotubes we can grow per unit area, for example, right?
Yes.
It looks like you have very, very powerful technique, and I'm hoping that some of this can be translated. Some of the approach can be translated to answer some of the questions we have. So my first question is, how do you scale it down, right? So if I really care about sub-micron dimensions, right, is this technique still applicable?
Yeah, I tell you what, so what you're describing is probably, so you can do it, but you're talking a lot about catalyst control in order to get the chiralities that you care about. The ARES system, which is the Air Force Research Labs system that they use with the Raman spectrometer, they have tried to do something similar to that. They used kind of in between the papers that I cited there. They've got one in ACS Nano, I believe, where they tried to answer that question. They tried to march through and synthesize whatever, I don't remember what the chirality was, but they wanted to understand the mapping between all these process parameters and the chirality of their CNTs. So they've done that in terms of trying to map out how the process is going to map to the chiralities. But what they haven't done is kind of the final piece of that puzzle, which is do it every time, do it exactly where you want to do it.
Right.
They haven't done that. So is it possible? Yes, I suppose it is. It's going to take some forethought about how you can manipulate your catalyst to So
this is really good because one of the things we're trying to encourage is sort of trying to find a new approach for future research, right? The industry community in general, I think will have we've been collaborating for far out future research with DARPA, right? And there will be a call for research coming out in about a month. Right, and we really desire to have some sort of a way to accelerate materials research, chemistry research, and unexpectedly, I think I should have thought more about this idea of autonomy, right? Autonomy to quickly identify the optimal process conditions that we can use to deposit the desired material.
Yes,
we're definitely lacking in those, right? And I'm really sad that the two communities doesn't seem to be talking to each other, right? Had we known about all this progress, maybe we could have been a lot faster in some of our own, internal research. So this is very fascinating.
Even if you take the machine learning algorithms out of it, if you could create a process that's high throughput and automated, 24/7 you're getting results. That's that's a big deal.
So I see it that I did a survey and I gave sort of a perspective talk to the community, the semiconductor community, that that the high throughput experimentation should be looked at, but we also realized that that by itself is not enough, right? We need a closed loop between the HTE characterization algorithm, right? The algorithm can be machine learning plus first principle calculation, and close the loop. And there's a very, I think, recent example on perovskites materials research at MIT that successfully combine all these components, right? So going forward for the what we need, right? we're trying to encourage this kind of a research so that we have a deeper pipeline, materials pipeline that we can draw upon for our device research.
Yeah.
Right now, our device research sort of masquerading as a materials research also, right? And you know, we're not being very optimal, in my personal opinion. Right? My second question is on the. You showed very nice examples, I think it's somebody else's work, where we have silicon pillars, right? Micro pillars, right? That we can use to do spatial separation and do individual, or sort of do sort of characterize or trying to induce different properties or different materials on top of the each pillars. Right?
Yep.
So I thought that would be a very neat way to, either as a second version of the HDE, right? Right now, HDE mostly is done on a flat substrate. Everything is mumbled, it's kind of jumbled. We have a composition gradient, right? And what we're looking for is one specific composition among those thousands, right? So, what is your thought about that? And my second question is that, is this useful for, maybe we can use this to help our chemistry discovery? Right, so we want very good CVD ALD precursors. It will take years, right? That's the state of the art with the best researchers, the best companies, the best applications, everything known. It will take 5 years to develop one, right? Yep. Is this a way to accelerate that?
Well, I think it is. So for the second part of your question, maybe it's a similar approach, but using DFT and atomistic approaches might be better for that. If you're looking at, coming up with an optimal composition, it might be hard experimentally, in a practical matter to do that. Okay. But the first part of your question, maybe you saw me laughing. It's exactly what we're doing right now.
Good.
We've got so those pillars. Yeah, we're putting down basically a gradient in catalyst, so that on a single chip, we should have a pretty vast compositional change in our carbon nanotubes that we grow. Yeah, and so the plan is basically a physical representation of what we did numerical. So, get SEM images of all these different compositions, compress them using a nano indenter to get all the mechanical things that we care about, and then march through this process with the experimental data, just like we did with the simulated data.
Okay. All right. I think we should. I don't want to take too much time here, but I'll be very interested in knowing more. And just maybe as a closing comments here, we're interested in many different types of materials, but mostly these are not bulk materials. These are thin films or nanostructural materials. We're interested in conductors, metal conductors. We're interested in dielectrics, low-K dielectrics. We're interested in what we call thermal transfer or heat transfer material. So something that conduct heat without conducting electricity, right? Right. We're interested in thermoelectric materials. We're interested in RF insulators, right? So there are many needs where we're sort of running out of materials. The materials that we know today, or we can engineer today, does not let us get to where we want to go 10, 20 years from now.
Yep.
Right. So, all right. Thank you so much.
I just want to add one thing. So, Harsono, nice to see you. Right, we've connected, but not.
Yeah, thank you. Yeah.
So Matt, tremendous talk. I'm not going to ask a question. I know in the sense of time, right? We can connect. I come from the materials side, so I'm EMD Electronics. Harsono and his company are one of my big customers, right? But I echo everything Dr. Simka said. I think you said it, Matt, and I think you're hitting on it. Is sparse data sets in R&D are difficult, so you've got to get into high throughput. But it goes hand in hand with AI. It's kind of like the two pieces of the puzzle here. So I think there's huge opportunity here on the material side. So. Thank you for the work. It's very nice.
Yeah, and I wish I could have gone into more detail. I kind of had to buzz through everything. But yeah, it's kind of a playground for me too, by the way, because there's so many things that you can do. It's fun. It's fun to think about.
Thank you.
Thanks again, Matt.
Yeah, thank you.
Yeah, thank you, Matt.